Welcome back.
How are you?
Thank you for making it so early. It's not cold. Was there ever winter over here?
Yes.
I don't believe it.
1 week ago.
I think everybody's lying.
1 week ago.
Yeah.
Last Sunday.
Okay, morning, everybody. Yes. Usual rules of class. Please shut your laptops, your phones, everything. Uh, why do I have an echo? Is there an echo? Yes, there is.
Oh, no.
No, but there was a poll because we need to know who's in class. Sorita, you made a poll for the attendance, right? Just release it and write down the number. That's 257, correct? Okay. So, all right, everybody. I think the echo is done. Shut your laptops, please. Shut them properly. Can you shut your laptop? Yes. Thank you. Right? This class is supposed to have 250 people, of which about 120 are supposed to be in this classroom. So it's disconcerting that I find barely 40 out here. I hope to see more in the next class. Everybody, there's a poll. There's a Piazza post 257. Please get on Piazza. This is the only thing that the polls are the only thing that you're allowed to open your laptops or phones for. And mark your attendance because that's how we're going to be taking attendance when you're here for those of you who are in class. For those of you who are in Zoom, please mark your attendance anyway. If you don't do this on the Piazza poll, I can still get it off Zoom, but I would rather not because Zoom tends to be noisy, right? Justin? Hi. So again, Piazza poll 257, right? Or post 257. And once you're done, please shut your laptops, right? So, okay. Okay, so sorry, not I'm sorry, it's at 246. Yes, much better. Okay. At some point in the middle of the class, I'll pause briefly and pass out pieces of paper for you to make name tags, okay? Let me begin in the meantime, because we'll run out of time pretty quickly. So, can anybody remind me what this business of training a neural network was all about? What were we trying to do?
Parameters.
Setting the parameters for what? Yeah, but what was the objective of setting up the weights and biases? Minimizing error between what and what?
Target function and our estimation.
The actual target function and estimation. Shut your laptops. All of you guys, if you're done with the post, shut it, please. Yeah, because I like to have laptops shut because if one of you keeps it open, eventually you'll sort of wander off and look at posts. Can you shut your laptop, please? Thank you, right? Eventually, you can't help it. You will wander off. You will look at Facebook. You will look at Twitter, something. And then it doesn't just distract you, it distracts everybody around you. Can you shut your laptop, please? Attendance. Yeah, just finish that and shut up, okay? You shut it, right? Okay. So now, when we speak of minimizing the error, what were we minimizing? What was the error we were trying to compute in theory, in principle?
Like the difference between the desired output and
Where?
actual estimation
Where?
after the output layer? The last
After the output layer, no, but which part? So this was the integral over the entire space, right? This was what we wanted to minimize. Do you remember that? And so what are we doing when we actually perform try to train the network?
Like points, the samples that we have.
So we're picking only some samples because we do not know the actual function itself. And so here is the situation we had. We defined a divergence between the output of the network and the actual desired output of the network at all of our samples. We took the average of this error over all of our training samples. The hope was that if you got everything right on the average, shut your laptops, guys, please. Okay. So the idea was that if we managed to minimize this loss, we'd learn a function that was correct at least at these points. And the hope was that if we managed to get it right at these points, it would be right everywhere else, right? So now, lady at the back, don't look at your phone. Please turn your phone upside down. No, yeah. No phones, okay? Anyway, now if I have all of my training points, thank you guys. Give everybody a sheet. Joshman, give me one sheet. I'll show everybody what to do. Thank you. Okay, guys, here's what I want you to do. We would have done this 2 classes ago. Each of you will get a sheet of paper. Fold it in half like so. And then fold each half inwards like so. If you're wondering what I'm doing, you'll find out in a minute. And so now you have this. You're going to carry this for the rest of the semester. You will write your name in big, bright characters so that I can see it from out back on both sides. And then stick it up like this so that it now forms a name tag and I will know who you are. Okay? Please do that. Let me continue. So, okay. So when I define my loss in this manner, if I have my training points, what is it a function of? What is the only thing that I'm allowed to vary which will change this loss? Anybody? Yeah? Everything else is fixed. The training data are fixed, right? Okay, so this is the problem that we have. We are trying to optimize the weights and biases, the parameters of the network such that this average error over training data, which we call the loss, was minimized. Now, I'm going to go a bit late. So this is a function or instance of function optimization. You have a function. It's a function of the network parameters. We are trying to optimize it with respect to network parameters. So now we can actually look at this issue of function optimization. And even before that, derivatives, right? So when I speak of the derivative of a function, what do I mean? Can anybody tell me? The gradient. That's still only terminology. What does it mean?
for a small change in input, like how much is the output change?
Exactly. The derivative of a function with respect to an input quantifies how much a small perturbation of the input changes the output. So if I have a function y equals f of x, at any x, if I perturb my x by delta x, the output y is going to be perturbed by some delta y. And how do I quantify the relationship between these two? I have a perturbation delta x, I have a perturbation delta y, right? How do I quantify the relationship? I can say there is a multiplicative constant if the function is smooth, if you get close enough. And if you look at a small enough region, eventually the function is going to be linear. And so we can say that delta y, the change in the output in response to a perturbation delta x of the input, is related to delta x through this multiplicative constant alpha. So delta y equals alpha times delta x. And this term alpha is the derivative. This is the only correct way of defining the derivative. How do you normally write your derivative in school? dy over dx. Would that work everywhere? Why not?
Continuous functions.
You assume the function's continuous. Would that notation work everywhere? Can I say alpha equals delta y over delta x? It's continuous still, right? What if x is a vector? Can I write 1 over a vector? You cannot divide by a vector, right? Can you? There's no notion of division by a vector. How many of you think you can divide by a vector? Can you shut your laptop back there, please? Shut your laptop. You there in the red? Yeah. Yes, please shut the laptop. Thank you. So, yes.
It's divided by a vector.
You did not divide by a vector, right? So the notation was kind of meant for simplification, but you've been through linear algebra. You cannot divide by a vector. So the notation dy over dx does not work everywhere, except when x is a scalar. A more generic, a more reasonable notation is f prime x. Even in that case, why is f prime x a better notation than dy over dx? Anyone?
Because it shows that the y is actually a function of x.
It shows that the slope, the derivative, depends on where you're computing the derivative itself. So there are two things. Dy over dx doesn't work unless x is a scalar. And even then, f prime of x is a more reasonable notation. Now, so consider a scalar input x. The derivative dy over dx is telling me how much a small increment in x, or how much a small perturbation of x is going to perturb y, right? So if dy over dx, if the derivative is positive, will an increase in x increase y or decrease y? If the derivative is positive. And if it's negative? Decrease. So wherever the function is increasing, the derivative is going to be positive, because dy over dx, x, y both have to be positive. And if it's decreasing, then this derivative is going to be negative. Where the function is flat, this is going to be 0, right? Same thing. When I go from scalars to vectors, the same concept holds. So here, if I have, now if the input is a vector, let's consider a two-dimensional vector. Then the input is going to live in a two-dimensional space. If I'm at any point x, now when the input is a scalar, there's only one definition of delta x. You're either moving forward or backward, right? In this two-dimensional case, how many different delta x's can I have? 4? X is the entire vector, is it not? So how many different directions can I take an incremental step in? 2? 1, 2, 3, 4, 5, 6, 7, 8. How many can I take a step in? Infinite, right? So how do you define the derivative in this case? There is no unique direction in which you can increment. From any point, you can walk in any point. And in this case, the change in x is also going to result in a change in y. And the direction in which you walk is going to define how much y increases or decreases, right? And so once again, you're still going to use this relationship, delta y equals some alpha delta x. And now you can see y, if delta x is a vector, I can't write dy over dx for alpha, correct? And so the same relationship still holds. But then if x is a column vector, then what is delta x? What will the shape of delta x be? I've just given you a hint. If x is a column vector, what is delta x? Write your name on your tag.
I don't have a pen.
Okay, borrow a pen from somebody, please. Thank you. I want to this. So if y is a scalar function of x, then what is delta y? Y is a scalar, right? It's a function, it's a board. So what is delta y? Is it a scalar or a vector? Scalar, correct. And so I have delta y, which is a scalar, equals alpha times delta x, which is a vector. What is alpha? What is the shape of alpha? It should be a yes. What kind of a vector is that? What's your name? Arushi, thank you. So what kind of a vector is it? It's a row vector, right? So you can see how this relationship holds. If you transpose everything and work off row vectors, then will the derivative come before the vector or after? If x is a row vector, then how would you write delta y? It is going to be delta x times the derivative. In that case, the derivative is going to be a column vector, because you have to multiply a row vector by a column vector to get a scalar. This is a notation of these sizes and shapes working out. So you at the back, do you mind shutting your laptop, please?
Sorry, I'm just done.
Yeah. So, okay. I'm going to assume a column vector notation. And so alpha is going to have as many dimensions as x itself. And then I can write delta y in turn as alpha 1 delta x1 plus alpha 2 delta x2 and so on. This making sense to everybody? Everybody? Okay, now what is alpha 1 in this case?
It's the derivative in the direction of delta x1.
So remember, delta x can be in any direction, correct? So suppose I choose delta x to be along the horizontal direction only, then delta x2 is going to be 0, correct? Then alpha 1 is going to be how much is the ratio of how much y changes in response to a small change of x1 when all the other x's are fixed. So it's called the partial derivative with respect to x1. Alpha 2 is going to be the derivative with respect to x2 when all the other directions are fixed. So when your step is in this direction, right? And so more generally, alpha, this derivative, is going to be a vector of partial derivatives. Everybody with me so far? Right. And so I can write my derivative as nabla xy, different notations. I've written it in this manner to show that the derivative is a function of x, and it's a derivative of y with respect to x. It's going to be a row vector, and it will multiply your delta x to give you the corresponding delta y, and the derivative, of course, is now a row vector where each entry is a partial derivative. That makes sense to everybody? Okay. So now, how many of you have heard the term gradient?
Yes.
So how do you understand the term gradient? Pardon me? So why is that? How is that related to the derivative? Okay, so the gradient as we define it is going to be the transpose of the derivative. So right here, I've said delta y, or I've written this as d of x, is going to be the derivative times dx, correct? Now, if x is a column vector, the derivative is a row vector. The transpose of the derivative is going to be a column vector. The gradient is a transpose of the derivative. It has the same shape as the input. Okay, we will use the gradients all over the place. Now, how does the gradient relate to derivatives, and what does it tell us? Now, look at this. I can say delta y equals the gradient, the derivative. I'll just call this alpha, which is dou y by dou x1 dou y by dou xn times delta x1 through delta xn. If I write this as delta x, this is a vector. If I write this as whatever my derivative, this also is a vector, correct? So this is a vector in a product. Everyone agree? Right. So now, what is a vector in a product? So let's say this is my derivative, delta xy, and this is my delta x. Because I can take a step in any direction, correct? So what is the derivative over here? What is the inner product? You remember the value of the inner product. What is the inner product between two vectors?
Time cos theta.
It's the cosine of the angle between them.
It's going to be magnitude of nabla xy times magnitude of delta x times cos theta. Right. And now remember, delta x can be in any direction. The derivative has a fixed direction. Delta x can be in any direction. So given this, right, when is the increment delta y maximum? When theta is 0, right? In other words, the gradient has the direction that delta x must be in for the function to increase fastest. That makes sense? Right? So the gradient is the direction of steepest increase, and the amount by which it's going to increase is going to be the magnitude of the gradient. Or does that make sense to everyone? Yes or no?
Yes.
Okay. And so the gradient is the direction of fastest increase in x. So if I have a multivariate function, y equals f of x, is going to be, for two-dimensional inputs, it's going to be some surface of this kind. At any point x, the gradient is the direction in which you must take a step if the function must increase fastest, right? And if you want the function to decrease fastest, you're going to take a step in the opposite direction, right? And at maxima and minima, where the function is flat, what is the gradient going to be? It doesn't matter which direction you move, it's not going to change, right? So there's another property of gradients that we will often use. If I have a sheet, right, I can slice it at any height. If I slice it at any height, what will I get? I get an edge, do I not? At that height. So that edge is called a level set. It's the value, it's the set of all points at which the function has the same value. It's level. And the level set is going to be a continuous curve also. And the gradient at any point is always going to be at 90 degrees to the level set. Make sense to everybody? Yes, okay. There's a second thing called the Hessian, which is the second derivative. I won't get into that. But first, we have a pole. Here's a post number 236 and 237. Yes. Yeah. That is the only thing for which you're allowed to open your laptop.
Recording in progress.
Set up a timer. Right. Yes. On Piazza. Wait, people are not finding the Piazza poles? Okay. All right, guys, I think the polls are open. We're going to run out of time, so let me begin asking for answers. Someone on Zoom, can you answer the first question? At any, select all the true statements. At any location x, there may be many directions in which we can step such that f of x increases. True or false? Somebody on Zoom? Is there anyone on Zoom?
It's true.
Okay. What about the second statement? True or false? Also on Zoom.
True as well.
Pardon me?
True as well.
True as well. And what about the third? Okay,
That
someone
is
in the
false.
class. It's false. Why? It's a transpose. Thank you very much. Second one, somebody in the classroom. If f of x is a scalar function of an n cross 1 column vector, then what is the shape of the derivative of y with respect to x? It's a 1 cross n vector, right? It's not a scalar. So everybody has got it right. Okay, guys, shut your laptops again, please. Let's continue, right? These are the statements that are true. And so the problem of optimization is as follows. You're given a function f of x of some variable x, and we have to find the value of x where the function is minimum. It could be a scalar function, could be a vector function. We're not going to make any claims about the kind of function itself. And in school, when you found the minimum of a function, how did you go about it? You took the derivative and equated it to 0. Was that enough? Double derivative. How so? What was the criterion on the double derivative?
Should be positive.
Should be a positive, right? So just to remind you, I have another point. Okay, someone in the class, which are the true statements here? Third one, right? The derivative must be 0 and the second derivative must be positive. I mean, there are conditions where the second derivative may be 0 and it could still be a minimum, but we won't get into that for now, right? So there's something called turning points. At a maximum, the function does something interesting. The function which is initially increasing flattens out and then begins decreasing, right? So guys, can you shut your laptops, please? I know, just keep it partially shut at least so I know you're not working at it, okay? So the function, so as you approach a minimum along any direction, the function is going to keep decreasing and then it's going to turn and it's going to start increasing regardless of the direction that you approach it from. Otherwise, it's not a minimum. Similarly, at a maximum, as you approach the maximum, the function is going to be increasing. Then you hit the maximum and then it starts to decrease. So maxima and minima are turning points. And our job is to find turning points. Now, the effect of these things being turning points can be seen on the derivative, right? Right here, right until the maximum, if it's a maximum, the slope is always positive, regardless of which direction you come from. And then after the maximum, the function begins to decrease. So the slope is going to be negative. Similarly, at a minimum, initially the slope is going to be negative. And then after you cross the minimum, the slope is going to be positive. At the minimum or the maximum, the derivative is 0. The derivative itself is going to be insufficient to tell you which way you're going. But then you can see that this red line, which is the derivative line, has a negative slope at the maximum and a positive slope at the minimum, right? And so when you look at the second derivative, it's going to be a negative at maximum and positive at minimum. So these are the tests we typically run. So when you want to find the minimum of a function, the general solution is you're going to try to compute the derivative, equate it to 0, find solutions. Then at the solution, you check the double derivative to determine if it is a positive or if it's positive or negative, right? Now, again, it's not so simple. First, derivatives of functions of a single variable. All locations with 0 derivative are critical points, but not all critical points are minima or maxima. So you can have inflection points where the derivative is 0, but it's neither a minimum nor a max. So at a maximum, you're going to find that the derivative is going down. At a minimum, you're going to see that the derivative is going up. At an inflection point, typically you'll find that as you approach the inflection point, the derivative has some value, positive, then it flattens out and becomes 0 and then goes back to being positive. Or alternately, it may start off being negative, as in this case, and then it's going to go back to being negative. So that would be a typical inflection point. And for functions of multiple variables, this gets much tougher. And this is where Hessians and such like, if you have ever encountered them, come in that if I have a function of 2 variables, then I can have a situation where as I go along this direction, the function is a minimum. But as I go along this direction, the function is a maximum. Can you visualize a function of this kind? Anyone?
Like a saddle?
Like a saddle, right? A saddle is a bowl. In one direction, it's going to be a minimum. In the other direction, it's going to be a maximum, right? So things are much more complicated for the multivariate functions. But regardless, the optima are still turning points. That's where the function changes. And it changes regardless of which direction you approach the minimum from. And so when we want to find the minimum of a scalar function of multivariate inputs, we're going to try to find the location turning points, meaning the locations where the derivative, the gradient, is 0, right? Now, once again, there's a simple way of solving it. And the way you can solve it is just compute the gradient. It's a nice function. If it has a nice functional form, or the derivative, equate the derivative to 0, you're going to get a bunch of equations. You could technically solve it. And then you have to determine whether it's a maximum or a minimum. And now here's where the Hessian bit comes in. And the Hessian bit is like so, that if I have a function, then if I have a saddle point, for instance, if I have a saddle, so the saddle, what does the saddle look like? The saddle is going to, it's going to be a bowl. It's very hard for me to draw these, right? So that's going to be something like this. Correct? So along this direction, this is a maximum. But along this direction, going in, this is a minimum. That's a saddle, right? And so here, I'm going to find the derivative to be a 0 at that point. But then, is it a minimum? Yes or no? Is it a minimum? No, right? There are places where the function is lower. So how do I decide? This is where you look at the Hessian. The Hessian is going to give you the two critical directions. The eigenvectors of the Hessian will tell you that the two directions of main change are this and going into the page in this particular case, right? Regardless of the orientation of the saddle, it's going to give you the primary directions of change. And if you look at the eigenvalues of the Hessian matrix, it's going to give you the curvature along those directions. And what would you find over here? What kind of eigenvalues are you going to find for the saddle? Negative? Along this direction, it's a minimum. It's a maximum, right? So along this direction, what is the curvature here? The second derivative is going to be negative. Into the page, it's a minimum. So the curvature is positive. The eigenvalue is going to be positive. So the eigenvalues of the Hessian, the eigenvectors, tell you the direction of maximum change. And the corresponding eigenvalues will tell you whether it's a maximum in that direction or a minimum. And if you have an absolute minimum, what would it be? What would these eigenvalues be?
They would be positive in all directions.
They would be, all the eigenvalues would be positive, right? So the test you would run is to equate the derivative to a 0 and then compute the Hessian and compute the eigenvalues of the Hessian at that location. If they are all positive, it's a minimum. If they're all negative, it's a maximum. If they are mixed, it's a saddle point. That makes sense to everybody? Yes. Okay, you at the back. Can you shut your laptop, please? Okay, you there. Can you shut your laptop? Thank you. If you must keep your laptop open, then go outside, finish your work, then come back. You want to keep it open here, okay? So the problem is you can't always find a closed form solution of this kind. It's not going to work. So the function may have an intractable form. In this case, iterative solutions are required. And the way the iterative solutions work, if I have an ugly function, neural networks are very ugly functions. You can't simply differentiate it and equate it to 0. You're going to start off from some initial guess and say, this is my minimum. Then you look around, check if it's a minimum. If it's not, you take a step. Then check again, and you keep doing this till you actually find it a minimum. And there are some questions. If I start at some point and I don't know whether I find it's not a minimum, I have to decide which way to step, and how big the step must be. So that's something to decide. So here's how it's going to work. I'll consider a scalar function. I'm going to start off a scalar variable. I start at some point. I find it's not a minimum. How would I find it's not a minimum? Anyone? The derivative is not going to be 0, for instance, correct? So then, suppose I have a function, and I find it's not a minimum. I have an x. Then if the slope is positive, if I take a forward step in x, will I be increasing the function or decreasing the function? If I take a backward step, so if I find that it's a not a minimum, and if I find the slope is positive, which way do I have to move? Backwards. So I have to take a step backwards. Now, if I find the slope is negative, if I take a step forward, will the function increase or decrease? Decrease, right? Simple, right? So here is a simple rule. I can just check the derivative. If the derivative is not 0, it's not a minimum. Then I can check a slope, check the slope. If the slope is positive, I take a step back. If the slope is negative, I take a step forward. Easy, right? Can I write both of that in a single formula? Oh. I can do that like so, right? I can say x minus sine of the derivative times step. That works too, right? It's the same formula. And then I can do one thing, make it slightly smarter. I can say x minus derivative, some constant times derivative. And observe what happens. If the derivative is negative, you're going forward, because minus and minus become plus. If the derivative is positive, you're going backwards. And the step size is going to be dependent on the magnitude of the derivative. Now, this is something very interesting and important. Your ideal function has a shape of this kind. If you have other shapes, you're going to have problems. You're going to have very unstable, it's going to be very unstable when you want to try to find the minimum. And so if you find, if this means far away from the minimum, the function is going to be steep. So at that point, do you want to take big steps or small steps? Big steps, right? Because you're far away. So you can take a big step and go boom, all the way here. Out here, do you want to take big steps or small steps? Otherwise, you might overshoot. And so that naturally goes into this update rule. Make sense? Everybody? Yeah. Thank you. Okay. Someone on Zoom want to answer this question? Zoom?
The first two.
Second? Wait, this is the same poll, right? Yes. Oh my God, I made a mistake. Okay, guys, you got lucky. All right. Sometimes, actually, I very often make mistakes. So this was your chance to make up on a broken poll. Anyway, so here's where we've got, where you've got multivariate functions. The gradient is the direction in which the function increases fastest. Going in that direction increases the function. Against the gradient is where the function decreases fastest. And going in that direction decreases the function. And so just following the principle that we just saw, if I'm trying to go to a minimum, which direction do I want to walk in? I want to go in a direction where I'm guaranteed that the function is decreasing, right? So what would that direction be? Opposite the gradient, right? And so I'm going to take a step against the gradient. Everybody with me so far? And if I want to maximize the function, which direction do I go? In the direction of the gradient, yes? Okay. So, Cyan, can you shut the laptop? Thank you. Fully. So, when do we stop? When do we stop? We keep taking steps. You can stop when the derivative goes to 0, but that's not a very good answer. And so Vedanta is right. You want to stop when the change is minimum, right? And we'll see why that is the case. So here's the overall gradient descent algorithm. You start off at some point. At each point, you compute the gradient and then take a step against it and keep doing so until the function keeps decreasing. Questions? Yeah.
With this, you get stuck in like local
We'll get to that. There's a lot of that we deal with, right? And so for appropriate step size, for convex bowl-shaped functions, gradient descent will always find the minimum. For non-convex functions, like the one that I have over here, it can get stuck in bad places. And there are a lot of heuristics for dealing with these, which we will see in coming classes. This is fourth of final 5 poles, but this is a genuine pole. It's not a duplicate, I think. I'm not looking at it. Yeah. This is not the final pole. This is my third authentic pole. I'm not sure what happened with pole 3. There was a different pole. It just got repeated. Okay, time. Anybody want to answer this question? Okay, yes. Yes, you want to go exactly opposite the direction of f of x at x0. Everybody with me?
Yes.
Right, okay, so this is a brief detour into function optimization, right? Let's get back to our problem. We want to minimize our loss, which is the average divergence over all of the training points. This is a function of the network parameters. And clearly, we can use the principles that we just saw to minimize this function, right? And so here's what we can do. Same principle. I can initialize my network parameters and then keep updating them at each time. I'm going to try to take a step against the derivative, against the gradient of the function, of the loss with respect to the network parameters. So, and we will continue to do so until the loss no longer decreases. This is our gradient descent algorithm. But before we proceed, we have to define a whole bunch of things. Here is my loss function. This is the function that we're trying to minimize. What are all the unknowns over here? What are the things we must define? I've given you a bunch of images and their labels. And now I want you to design the loss function. How are you going to define it? Anybody? What are the things that must be specified? Remember, this is math, right? Step size, we're going way ahead, right? Let's look at the things we must define. What are these input-output pairs? Images and labels, are they numbers? Are images numbers? Are labels numbers? Are classes numbers? So we have to figure out what these things are. How do you convert them to numbers, right? What is this function f? What is our network? What are its parameters, right? And then finally, what is this divergence function that we are using to compute the error between the actual and desired outputs of the networks? All of these must be specified. And specifying this is, without doing so, you can't really solve this minimization problem. So let's start with the easiest thing first. Our function f, this is going to be a multi-layer perceptron in most cases, which is directed and has a set of inputs and a set of outputs. As we saw in the last class, a multi-layer perceptron is a function with parameters w, easy, right? So we're going to assume a layered network for simplicity, because every network is effectively layered eventually. But what I mean by this, we are saying is that more often than not, we're going to assume that all of the output neurons are the same layer. Then the inputs, there are no neurons over here, but we're going to call them the input layer, just because that's terminology. These intermediate neurons are units whose outputs you don't really need to inspect. You're only interested in the output. So we will call them the hidden neurons. And these are the hidden layers. And this guy, whose output you're actually trying to read, is going to be called the output layer. The individual perceptrons, the individual neurons, I'm going to use the term perceptron and neuron interchangeably, are going to be like this. As before, they first compute an affine value, which is a weighted sum of all of the inputs. And then this affine value is going to be put through an activation function. And we've seen in the last class that threshold activation functions are not great, but we're going to generally have a differentiable activation function. So this is the standard case, but more generally, a perceptron can be any differentiable function of the inputs. Okay? So, but we're going to assume units which first compute an affine value and then apply an activation to it unless otherwise specified. So here are some typical activations. You have the sigmoid activation, which is 1 over 1 plus e raised to minus z. It goes from a small value up to a large value smoothly from 0 to 1. The tan H activation is basically just the sigmoid scaled to have a dynamic range of 2 and centered at origin. So, and then you have other activations like the ReLU, which is 0 for negative inputs and equal to the input for positive inputs, and the smoother, fully differentiable version of it, which is the soft plus. And we also have their derivatives on the slide for each one of these. Now, one thing I want you to keep in mind, there's no need to memorize the equations for derivatives. You can always look these up. But then something that must be remembered is, what is the concept of a derivative? A derivative tells you whether increasing the input increases the output or not, and by how much. So long as you remember this, you can sort of intuit the behavior of the network and its units. And this is going to be very important, right? So now we can also have neurons which have multiple coupled outputs. So I could have, for instance, a when I have a layer, the way we set it, you have all of these inputs, and here there's a z value that goes in and a y value that comes out, right, for each of these. So zn, yn. So this is how we have defined our layer so far, right? But then I can generalize this. I can say instead that I have all of these z's, z1 through zn, and then there's a generic block from which I get outputs y1 through yn. So what is the difference between these two? Here, if I perturb z1, will y2 change? No, right? So each output is going to be dependent only on its local input. In the generic case, I can design networks where if I perturb zn, y1 could change. Right? So this is a generalization of the simple scalar network. And yes?
Within this diagram that we've been seeing all along, every other neuron is connected to the other neuron, so a change in one does affect.
No, but with locally, I'm speaking of an activation function. But these are just the activations, right? And you can compute an affine value at each one. So if I change this w, for example, perturbing this w will perturb this y, but not the other y's. Whereas in this case, if I perturb a w that goes in here, all the outputs could get perturbed, right? And so one very common activation function of this kind is the softmax activation. Have you encountered it? Where? You've begun your homework, I assume, right? Have you encountered the softmax? So how did we define the softmax, guys? Anybody?
Usually maps your entire input values between the ranges of 0 to 1.
How did we define the softmax? Somebody at the back. Maybe I'm going to ask you, right, Vishnu? How did we define a softmax?
It was 1 by 1 over 1 by 1 plus exponent of c.
So how many outputs does a softmax have? Julio, how do you define
Shape of the input.
same shape as the input? Yes. So what was the equation for it?
So basically, each piece of the input is exponentiated and is divided over the sum of the exponential.
Correct. So the way we defined a softmax was we said that yn equals e raised to zn divided by j e raised to zj. We exponentiated each of the z's So you got the exponentiated terms on the outside, and then we normalized it so that they sum to 1. Everybody remember this? Well, if you haven't seen your homework and if you haven't done this before, you probably won't remember it. But then this has got to be burnt into your mind. Okay. Now let me ask you about derivatives. If I think of this, of the derivative of y1 with respect to z1 over here, will it be positive or negative? What is the derivative of partial derivative of y1 with respect to z1?
Positive.
Why?
Because the function is like it's a monotonically increasing function.
Yeah, that's a good answer. But then, anybody else? Saha, what's the derivative? Is it positive or negative?
Positive.
Why are you in doubt? Look at this formula here. Will increasing z1 increase y1 or decrease it?
Increase.
Increase. So what's the derivative?
Rate of change.
Is it positive or negative?
Positive.
Okay, please pay attention, guys. What is the derivative of yn with respect to z1? Anybody?
Negative.
Why?
Increase the denominator but not the numerator.
So because, look at this. The way this is set up, all of the y's are going to sum to 1. Correct? So if any one of them increases, what must happen to the rest? They must decrease. So if you increase any z, the corresponding y is going to increase. The remaining y's are going to decrease. So the direct derivative, partial derivative is always going to be positive, and all the remaining partial derivatives are going to be negative, right? So the lady behind the red flask back there. Can you shut your laptop, please? You there? Can you shut your laptop? Yeah. Thank you. Please shut it. Close the laptop, please. How hard is this? Please shut it and keep it shut. Thank you. Right. Okay. So a typical network, in a layered network, each layer of perceptrons can so these are what we will call vector activations, where it takes a vector of inputs and generates a vector of outputs, okay? And every layer in a typical perceptron can be viewed as a vector activation, single vector activation. And so we've defined the function f, right? We've defined that it's the shape, and we've defined the components, which are the individual neurons and their activations. The next thing to define inputs and outputs. Now, in the case of inputs, there are and outputs, you have the actual input x, you have the network output y, and you have the desired output d. Now, the network output must have the same shape as the desired output. Otherwise, the network is not computing the desired output, right? So you might have d-dimensional inputs. You're going to have several of those. And you're going to have corresponding L-dimensional actual and desired outputs. And all of these must be defined. You'll have several of these. The first subscript here indicates the instance number. The second subscript indicates the dimension. But I won't use the, I'm just going to use only one index for the component. Now, the input is going to be a vector of numbers. Everything is numeric. This is the computer world, right? And so if the input is the scalar, then it can just be a single dimensional input. Otherwise, for pictures, you're going to convert it to a vector of pixel values. Pixels are numbers. You can convert it to a vector of pixel values. If you're looking at speech, the speech is some kind of a signal. First, you're going to put it through some process. You're going to compute some features out of it, which are numeric. Those are going to be your input. If you're working on text, text is not at all numeric, right? Then you're going to have to perform some operation on it which converts it to a collection of numbers. And then you're going to input it to your network. And if you're working on real valued inputs, no big deal. Those are going to be the inputs to your network. What about the output? Now, if you're just performing real valued regression, you're computing real valued outputs, no big deal. The output is a real valued number. What you want is also a real valued number. Everything works just fine. So there's no further definition required. And if the output is a vector of real values, then the network is going to have as many output neurons as the dimensionality of your desired output, and we're all good. But then, if you're performing binary classification, that means you have the output can take one of two values, 0 or 1, meaning it's either a dog or not a dog. You're going to assign numbers to it, 0 and 1. And so now you want an output layer which also outputs a binary value, either a 0 or a 1. So now we're going to have a single dimensional, single neuron at the output. And you're going to convert your binary classification problem to a numeric classification, 0 or 1. And the target over here is that this output activation, this also determines the output activation. The output activation must also output either a 0 or a 1. But then we know that if I just have a threshold activation at the output, which either outputs a 0 or 1, what happens? What was the problem with that?
Like you don't know how much to change it.
The derivative is either 0 or not definable, right? And so in this case, you're going to have an output of x, either 0, either 1, or 0. And we will typically use a sigmoid activation, which goes from 0 to 1. And the sigmoid activation takes a value between 0 and 1, and this can be viewed as the probability of class 1 given x. Now, if you wonder why this is the case, go back and look at the slides from last class. Right? Now, you can also see this from the formula. The sigmoid activation is 1 over 1 plus e raised to minus z. So if z is a large negative value, what is e raised to minus z? Say z is a very large negative value. Then e raised to minus z is going to be a very large
0.
E raised to minus z is going to minus z is going to be a large positive value, right? And what is 1 over a very large positive value? Very small value. If z is a large positive value, then what is e raised to minus z? Large negative value? Close to 0. Then what is 1 over 1 plus e raised to minus z? 1. And so you can see how this has to go from 0 to 1. And because it's continuous, it's going to take this shape, right? Everybody with me? Okay. And so now here's the other thing. Now, so we've defined our activation function. We can, what about the inputs? Or what about the multi-class case? So suppose I want to perform a classification where I'm classifying between, say, 100 classes. Or in this case, let's say I'm trying to distinguish between these 5 classes: cat, dog, camel, hat, and flower. These are not numbers, right? So I have to convert them to numbers somehow. So here's what I will do. I will arrange them in some pre-specified order. And then any instance of cat is going to be a vector with as many components as the number of classes, but only the component corresponding to cat is going to be 1. The rest are going to be 0. Similarly, any instance of dog is going to have a 1 in the dog at the dog index and 0 elsewhere. So each class has now become a vector which has as many components as the number of classes, and only the value corresponding to the index of the class is 1. The rest are 0. These are called one-hot vectors because only one element is hot. All the rest are cold, right? Now, so when I have a multi-class classification network, I'm going to have as many outputs as the number of classes. And the desired output is going to be a one-hot vector. So now I have converted my classes to a numeric format. And so when I have my multi-class classification network, it's going to be this entire network out here. This is my output layer. And in this case, I'm going to have, for my example, I'd have 5 outputs, right? And anytime I see an instance of cat, what is my desired output going to be? It's going to be 1, 0, 0, 0, 0. Anytime I see an instance of dog, my desired output is going to be 0, 1, 0, 0, 0. This is my desired output. That makes sense to everybody? Now, once again, what is the problem with having such a having activation functions which output either a 1 or a 0?
The input is none of them is classified as 1.
No, that's not the point. Yeah? If it's just 1 or 0, it's not going to be differentiable yet again, right? So what kind of activation would we want? A softmax. A softmax is going to give us, in this case, something where you're going to give a bunch of values y1 through yn, which sum to 1, and these can be viewed as the probability of the class, right? When the network is 100% sure, it's going to assign a probability of 1 to the correct class and 0 to the others. Otherwise, it's going to give you some intermediate probabilities. That make sense to everybody? Yeah. Yes, Karthik?
But this also, so what happens if you give an input, like you train model, you give an input that's none of these classes?
That's good. The network can only output one of these classes, right? You have no choice. And so softmax vector activation is often used as the output of multi-class classifier networks. And these can be viewed as the probability of the class given the input. In a class much later from now, we will actually look at how this thing happens, right? And so in a typical problem statement, you're going to be given a bunch of training instances, like images of this kind, and along with information about which digit the class the image represents. And then you can have different kinds of tasks. A binary classification task, is this 2, or is this the digit 2 or not? Or a multi-class classification, which digit is it? And in a binary classification task, you're going to convert all of your data into this format. Corresponding to each input, there's going to be a binary label, which is either 1 or 0. And if it's a multi-class classification problem, you're going to be assigning the actual label, class label of the instance, which, when you train the network, is going to be converted to what kind of vector? What will the one hot vector, right? Okay, which is what you will use. And so we've defined the inputs, the outputs, and the network function. Here's the last bit we have to define, the divergence function. Now, for the whole thing to be, entire thing to be differentiable, what is the requirement on the divergence function? Would it have to be differentiable also? Yes. Right? So again, so for the loss to be differentiable with respect to W, the divergence function must also be differentiable, correct? So let's look at different kinds of divergence functions. If I'm making real valued predictions, then the output is a bunch of real valued components. It's a real valued vector. And my predictions will also be real valued. And a very natural error in this case is going to be the Euclidean distance. The output is a vector, the target is a vector, the distance between the two is actually going to give you a vector also, right? And so now, let's look at any individual component of this, just to see how this works. What will the derivative look like? So let's intuit about the derivative, right? You find that y minus d squared is the same as d minus y squared. The order doesn't seem to matter, right? So why does the derivative have a negative or a positive value? Should the derivative with respect to y be different for d minus y versus y minus d? Doesn't make sense, right? So then if you get confused, here's an easy way to look at it. Let's say my desired value is d, right? And my current value y is greater than d. Will increasing y increase the error or decrease the error? So what is the derivative going to be? Increasing y increases the error. What is the derivative of the error with respect to y? Positive, right? It's got to be proportional to y minus d, right? If y is below d, then will increasing y decrease the error or increase the error? Decrease. What is the derivative? Negative. Once again, y is below d, so right? It's going to be proportional to y minus d. And so that makes sense to you guys? Just intuitively. And so the derivative is always going to be y minus d. This factor of half on the outside is a scaling constant which just sort of gets rid of the 2 in the exponent when you take the derivative. So it's a half, this half summation y minus d squared, that's how we define our L2 loss. Everybody clear about this? Questions on Zoom? Any questions on Zoom? No, okay. So for binary classification, we are going to use a different kind of error. Here, the output is either 1 or 0, the desired output. And the actual output of the network is going to be the probability, correct? So now, oh, where did I put my eraser? So let's say my target output D is 1. It's a binary classifier, right? The output is either 1 or 0. And now, if the actual network output is 0, Y is a probability, correct? It says there's 0 probability that the output belongs to this class. How wrong is it?
Entirely wrong.
Entirely wrong. Is it kind of wrong or infinitely wrong? Infinitely wrong, right? That makes sense to everybody? Right. Whereas if Y is 1, how wrong is it? It's absolutely correct, right? Now let's flip it around. If the desired output is 0, I'm saying it's not a cap. And my network says with complete certainty, yes, this is a cap. How wrong is it? It's infinitely wrong, right? So when we begin performing classification tasks, there's no such thing as somewhat wrong when you're completely wrong. And so the corresponding, now what kind of loss function would make this infinite? Infinitely wrong. Log of 0? Right, but log of 0 is minus infinity. So you need a minus, correct? That makes sense to you guys? And so here's what I can do. I can say minus d log y for the case where d is 1, minus 1 minus d times log of 1 minus y, in the case where d is 0. That makes sense to you guys?
Yes.
Right? Again, you're thinking of it in terms of probabilities. And it's saying you're making sure that you're absolutely, there's 0 error when you're right, and there's infinite error when you're completely wrong. This is the Kullback-Leibler divergence, right? Once again, over here, regardless, if the desired output is 1, right, and say y is 0.9, will increasing y increase or decrease the error? Decrease the error. So what is the derivative going to be? Negative, right? Now, on the other hand, if d is 1, if d is 0, and y is 0.9, will increasing y increase or decrease the error? Increase the error, right? And what is the slope going to be? Positive. So here's what you get, right? When d is 1, it's minus 1 over y, because the slope is always going to be negative. It keeps telling me to increase y. When d is 0, it's 1 over 1 minus y. It keeps telling me to decrease y. That makes sense to everyone? Right? Again, you can work through the math, but you don't really need to. If you understand what a derivative means, it all makes sense. Right? Now, why do we use KL divergence versus L2 divergence? Even for the case of classification, binary classification, I could have just used the squared error, right? But the problem with the squared error is this. This bowl over here, the red bowl is the squared error between the actual and desired outputs of the network. And the blue is the KL divergence. And you can see how the KL divergence says that when the prediction is the exact wrong thing, the error is infinite, whereas the L2 divergence is kind of meh. Yeah, I'm kind of wrong, right? It doesn't make a lot of sense. So, but then there's something else that shows up over here. So I have the error. I have the derivative, which is minus of 1 over y when d equals 1, correct? It always tells me to increase y. If y is exactly equal to 1, what is the loss in this case? 0, right? You're making no error. What is the derivative? It's minus 1, right? So was our initial assumption that the derivative is going to be 0 at minima correct? Right? Yes or no? Right? So when y is, similarly, when y is 0, right? And if the desired output is 0, what is the derivative? Yeah. What is the error if y is 0 and the desired output is 0? 0. But what is the again, what is the derivative of the function over here? 1, right? So again, you're going to find that the derivative doesn't always become 0 at the minimum, which is why when you're using gradient descent, you're actually going to be looking at whether your loss is decreasing any further or not, and not simply verifying the error, the derivative. That makes sense to everybody? Okay. And so for multi-class classification, I'm going to do something much the same. I'm just going to generalize this. And in fact, in binary classification, you can think of it as having two classes, class equals 0 or class equals 1, right? So the multi-class equivalent is I have many classes, and if di is the desired output for a class I is 0, then the desired output for j not equal to I, what is this going to be? If the desired output for class I is 1, what is the desired output for all the other classes? 0, right? So when yi equals 1, what will these y's be? 0, right? So again, if yi is the same as 1, I want the error to be 0. When yi is 0, how wrong is it? Infinitely wrong, right? What would be a good loss function which captures this? The log again, correct. And so once again over here, it's going to be minus of summation I di log yi. It seems like we are summing over all of the classes, but we are not really, right? When the desired output is 1 for one class, it's going to be 0 for all the other classes, right? So this eventually just ends up being a single term. And the single term is going to be minus of log of y of the correct class. Does that make sense to everyone? Because all the other d's are 0, right? And then again, going back to the derivative, if you're for any desired class, if you increase y, will the error increase or decrease? So let's say you want to say, firstly, suppose I have a multi-class classification problem. Is this loss a function of all the classes? Or is it a function of only the desired class? Only the desired class, right? So what is the derivative with respect to the other classes? Outputs. So what is the derivative? It's going to be 0. The other classes are not even figuring in this formula, right? What is the derivative of this with respect to the height of the Eiffel Tower? It's not part of the equation. It's going to be 0, correct? So this loss only has a derivative with respect to the probability assigned to the correct class. And will it be, and what is that derivative going to be? Positive or negative? Do you want to increase the probability of the correct class or decrease it? So what is the derivative going to be? Positive, increasing the probability of the correct class. Will it increase or decrease the error? Decrease the error. So you're going to find a loss, which is the derivative is 0 for all the other classes and minus 1 over y for the correct class. It makes sense to everybody, right? Okay, so it's easy to make sense, right? And once again, you'll observe that when the output y equals the desired output, the slope is not 0, it's actually minus 1, right? So again, this is telling us that it's not sufficient. It's not, you should not expect that the derivatives will be 0 at the minimum. They may not be 0, right? And here's one final thing before we close. That when I perform a softmax, what I am really doing is two things. I have a bunch of z's going in. I have z1 through zl. These are all my classes going in. I have my softmax. I have a bunch of y's coming out, right? And then on this, I have my desired output D, and I'm computing my Kullback-Leibler divergence. So the derivative that we just saw was the derivative of this divergence with respect to these y's out here at the output of the network. That derivative is going to be 0 for all the wrong classes, and it's going to be negative for the correct class, right? Which seems kind of counterintuitive, because should I not be decreasing the probabilities of the incorrect classes? I should be trying to do that, but the derivative says it's not necessary. That's because if I increase the probability of the correct class, the others will naturally go down. But then here's the crazy bit, that if I work out the derivative of KL with respect to these z's before the softmax, that one also simply ends up being y minus d. Right? Again, I won't work this arithmetic out, but we saw that in the case of the L2 loss, the derivative of the loss with respect, again, so you can think of the L2 loss typically when you're performing real valued computations, you're going to get z's, and then here you will just, the activation is typically an identity transform. You're not going to be performing any nonlinear operation on it. And then you're going to get a bunch of y's, right? And then on this you compute the L2 loss. This is for real valued regression. And so here, because you have an identity transform, the derivative of the L2 loss with respect to z is simply going to be y minus d. Okay, and which is the same as z minus d. And in the case of the Kullback-Leibler divergence too, the derivative of the loss with respect to z is also going to be y minus z. So in all cases, in both cases, the derivative is going to be just the error between the actual output of the network and the desired output of the network. So this is kind of pretty, that the derivative of the loss with respect to the affine values going into the final layer is always just the error, y minus d. You don't have to work out the math, you don't have to compute it. This is guaranteed. So when we actually compute derivatives and move derivatives backwards to compute the derivatives for the other terms in the network, what we will be doing is moving this, using the chain rule to propagate the derivative of the loss with respect to z backward through the network. But the derivative of the loss with respect to z is the error. And so we like to call this error back propagation. The error keeps getting propagated backwards through the network. And so we have all terms have been defined, right? Final poll. Guys, don't forget your name tags in the next class, and I expect to see everybody in class on Monday. Oops. All right, guys. So select all that are right. Somebody on Zoom, is the first statement correct? Zoom?
No.
No.
Second one?
Yes.
Correct. Okay, in the class, let me pick a random name, right? So Björnsson, is the third statement correct? That's you. I'm assuming that's your name, right? Okay, is the third statement correct? It's on the slides. Is the third statement correct? Yes or no? Okay, wake up. I'll be here to ask you in the next class. And Mangro, what about the fourth? Not correct. So does everybody agree with that? Okay. Anybody else have any questions? Okay. So, guys, I'll have my clicker in the next class, which means that I'm going to be walking up and down. I'll stand uncomfortably close to you and ask you questions. Do not sleep. Do not daydream. Do not let your brain wander. Because if you do, I will be there next to you and asking you a question. Okay? So the gradient may be 0 or close to 0 at the minimum, but it's not a guarantee. It may also have a large magnitude at the minimum, right? And so here is the story so far to wrap up. Neural networks are universal approximators. They're trained to approximate functions by adjusting their parameters to minimize the average divergence between their actual and desired outputs on training instances. To train them, we have to define several things: the network itself, the manner in which inputs are represented as numbers, the manner in which outputs are represented as numbers, and the divergence function that computes the error between actual and desired outputs, which is typically L2 divergence for regressions and KL divergence for classification. So in the next class, we'll talk about how to compute those derivatives and how we can use them. Right? Thank you for coming in on a Friday. I appreciate it. Thank you for coming in. Thank you for coming in.